while they're doing the swap there, I'll tell you a little bit about Tommy, for those of you who don't know Tommy. Tommy is joining us from TACC. He's the Director of Advanced Computing Systems. He joined TACC back in 2003 as a research associate, and over time has grown to the Director role of Advanced Computing Systems, responsible for organizing and coordinating activities within the ACS group, and to both operate and maintain production systems infrastructure of TACC. They've been a great partner of ours in a lot of DDN technology, IME being one of those, and so we're really enthusiastic to have you share your thoughts.
Thanks a lot.
Go ahead.
So I have kind of two topics I'm going to talk about today. First off, I'm going to give an update on what I presented last year, and that's our Stockyard file system. That is very similar to what Steve has deployed in data capacitor. We took the lessons learned there, and same thing that Joel has done now at University of Miami. I'm going to talk a little bit about that, and first off, just about TACC. I'm going to skip ahead a little bit. I know we're running behind on schedule, so if you're curious, go to our website. But really, our storage needs break down into three different categories here. So we have the cluster-specific storage. We really want high performance out of this. Large capacity. Of course, we may need to purge it frequently because users will fill it up. I like to joke that the disk drives our file systems have one of three states: brand new and empty, full, or dead. So you've got one points in the middle. So if you have to keep up with the purging to make sure you got enough storage for all users. The second one is the one that we just deployed called Stockyard, which is our center-wide persistent storage. Like many of the other sites, we had a lot of user demand for a central file system that they could access from a lot of different systems. We wanted a very large capacity. Of course, this is going to have a quote on it to prevent users from filling it up. We wanted moderate performance. We wanted it to be very reliable and high availability. So a lot of our design of the Stockyard system is really oriented around keeping it available from all production systems. So it is a little bit isolated. It's not directly attached, except through LNAT routers to any of the other production systems attached. And then, of course, we have the tape library, persistent archival storage. So we've had a long history with DDN at TACC. We've been deploying their systems for many years. Have worked together quite a lot with deployments. So our very first DDN system was actually on Lone Star 3, our parallel HPC system. This is where we got our feet wet, learned how to do deployments of the controllers. Then we realized that we needed to have some file systems that are more centralized associated with UT, so we deployed Corral. Corral at the time had 1.2 petabytes of disk. That was in 2008. Lone Star 4, we took our lessons learned from Lone Star 3 and upgraded to the SFA12k. We've actually increased it a little bit. We now have about 2.4 petabytes of disk behind 3 SFA12k controllers. And then in 2011, we upgraded Corral to also SFA12k with 5 petabytes of disk. And this is our only GPFS-based file system. And the reason for that is actually we do replication of data to a different site. The problem is Corral was for UT system users only. We support a whole community of folks through the Exceed project. Through National Science Foundation funding. And so we wanted to be able to make them have a very similar file system storage. So we decided to deploy a global file system. So we set up some requirements. We wanted the file system to be available from all the systems. So we issued an RFP, had several competing bids come in, proposals. We had some requirements. We wanted at least 20 petabytes of usable storage. We wanted at least 100 gigabytes a second of aggregate bandwidth. And we wanted the highest availability and reliability. We wanted to make sure that, typically in an HPC center, we're happy with 98% uptime. Well, we wanted more nines out of that. So we didn't want to expect 5 nines like a commercial shop, but we wanted to get closer to the 3 or 4 nines. So we, of course, selected the DDN proposal for the project. And what we ended up designing and setting up is a Veloster 2.42 based global file system. We do have scalability plans so that we can do future upgrades. We built it around a scalable unit. In our case, the unit is 16 storage servers and 2 SFA12k couplets and racks and all the disk drives associated with it. Each one of our scalable units will do about 25 gigabytes a second. So of course, we put 4 of these together. Gave us about 25 petabytes of raw capacity, greater than 100 gigabytes a second. And then we realized we wanted to be able to connect it to all of our production systems, so we deployed these, as part of the RFP, we actually had routers, LNet routers, included in there. So we have 16 routers that were included with the system for external mounts to other production systems. So just to kind of give you an idea of the scalable unit, what's interesting here is this is actually the real design in our data center, because we do have cooling units that sit between each of the racks. These provide supplemental cooling in addition to the underfloor cooling. One interesting thing we did stumble across is these are 50U racks. Well, when we built our data center, the doors were actually designed for 48U racks. It turns out that these racks are about a ½ inch too tall to roll through the door properly. So we did have to work with DDN to get some appliance dollies to tilt the units over so that we could get them in the door. But after that, we had plenty of space in the data center to house the racks. So our scalable unit design is SFA12k 50U rack. We actually do have 8 L630 plugs for each rack that provides all the power. We have an SFA12k couplet, 16 IB FDR ports, and these are directly attached to the OSS. We actually don't have switches in the way for the direct data attachments. We use the 84 slot enclosures, 10 per rack, so 840 drives per rack, 20 enclosures per scalable unit. And at the time we selected the 4 terabyte drives. These are the nearline SAS drives, but I guess now are available on at least 6 terabytes and even more. So just to give you an idea of the layout, so these are all the racks available on Stockyard. So over here are actually the production clusters. Everything within Stockyard, all the OSS servers are all connected on their own InfiniBand fabric. This is isolated from any other InfiniBand fabric we have at TACC. We have about 4 or 5 production systems that have InfiniBand, but we wanted to make sure as we're working on one system, maybe messing with the InfiniBand fabric, upgrading it, we didn't want to impact anything on the storage subsystem. So what we did is we designed LNet routers here to be able to expose and connect up to the various production HPC systems and visualization systems we have at TACC. One interesting thing we did is we actually left some space in the racks as well so that we could add LNet routers. So every time we add a production system now, we actually just add LNet routers to increase capacity and to control bandwidth to different production systems. So this is actually a picture of the install in the machine room. They do get some glass space, and those of you who know Ariel, that's Ariel actually working on one of the DDN racks right there. So, but the installation was very smooth. Everything went according to plan. Kept it on schedule. DDN delivered all the hardware as expected. And we actually got everything up into production. We got more than 20 petabytes of usable capacity. We did achieve more than 100 gigabytes a second to the file system, so we're extremely happy with that. As I mentioned, we can add LNet routers to connect into Stockyard for IB switches. Right now we support both FDR14 and 10dB. We are looking at 40dB, and once it gets a little bit more cost effective, we'll be adding in 40dB as well. And we set up everything with automatic failover using fluoroscopy pacemaker. This actually has been extremely effective. We have had failover events happen on the system, and it's pretty much seamless. No system administrator intervention required, and everything works very smoothly. Users don't even notice that the file system may have switched over, other than they have a bit of performance degradation. So as I mentioned, we did surpassed 100 gigabytes a second, but then of course we want to see how it really performs once we connect it up to the production system. So we connected it up to Stampede. It actually replaced one of the existing file systems we already had on Stampede that we called /work. This was a quoted file system. Users only got about 250 gigabytes of quote on that. And we could only do about 20 gigabytes a second to that file system. So when we first deployed it, though, one of the challenges was we were running a 216 Lustre client, and with the 16 routers, we were only getting about 65 gigabytes a second to the file system. We actually did some work and realized that there's some credit settings in Lustre that could impact your performance, and of course, in the newer versions, Lustre 252, they have a newer credit setting. We're actually able to get up closer to what we expected, which is the 75 gigabytes a second from Stampede to the file system. So, users were extremely happy. They didn't even notice we replaced the previous file system. We had rsync everything over, and then during one maintenance, we basically did the swap over. The only compliments we got were, hey, my quota increased, you got a terabyte now, you weren't limited to only 250 gig, and the performance improved. And we did have a couple of users notice this and say, hey, wait a minute, how come things are faster? It's like, well, you didn't notice, but under the covers, we switched everything out for you. So, we have recently added 8 LNet routers. This connects Maverick. Our Maverick is our new visualization system. And of course, now what this allows our users to do is they can write the data out to the Stockyard work file system, run all their data on Stampede, and then they can go straight over to Maverick and do remote interactive visualization using the GPUs that we have available on that system. So, users are very happy. They have now a persistent location. We've been working with them as well to make project areas available on here. In fact, we have, I know the Galaxy project has about 200 terabytes of data located in on this file system. And we continue to expand that as we add more and more projects and get more requests for central storage so that big groups of users can access the same amount of data. I mentioned the failover testing. We did actually do a fair amount of failover testing to make sure that everything worked seamlessly. We didn't want any interrupts on the system, so I have a few procedures in there of describing kind of how we did our failover testing. Everything worked seamlessly with the OSS servers, and as well with the MDS. We did it also with the metadata servers, and everything shows the recovery, and the client logs all recover, and IOs just continue. So again, one of the nice things about Lustre is it does have this mechanism for the failover testing. So the challenge we have, though, at TACC is the file systems are hardly ever pushed to their capacity. We've got a lot of capability, we've got a lot of bandwidth, but for 99% of the time, we're not pushing the max bandwidth that we have available on the file system. So what we really need is a lot of capacity with lots of spindles, but we need to be able to handle the burst of I/O. And this is one of the things that interested us when we first heard about IME and talking to DDN. So we worked with Gordon and Paul and several other DDN folks that had the idea of, hey, let's use Stampede to really test IME at scale. And let's see if we can really use IME in real-world production environments. So, luckily, I still have the old work file system hardware around. It is still available and still actually has about 50% storage and use on it. So what we were able to do is use that to evaluate IME, and we use the work file system as the back-end store. As all these you noticed, you put the IME as your burst buffer in between your compute and your back-end store. So just to give you an idea about the old Stampede work file system, it was 8 storage servers, 64 drives each. It's running a Lustre 252 version. This was actually our test bed where we test new versions of Lustre before we roll them out into production now. It was initially capable of about 24 gigabytes a second of peak performance. Unfortunately, as most of you probably are aware, as you start to fill up your file systems, they will slow down. You always get that fastest performance at the edges of the disk. And at 50% capacity, we can actually only sustain about 20 gigabytes a second to the file system. And that's peak, wind at your back, everything running smoothly on the hardware. So what we want to do is compare it directly. Let's say we deployed 8 DDN IME servers instead. In this case, they were fully populated with SSDs. There's 2 FPR IP connections per server, so we have 16 InfiniBand connections. If you do some rough math, about 5 gigabytes a second per port, you should see about 80 gigabytes a second of peak performance. This was just a rough estimate. But it was interesting because once we actually deployed it, started working on it, we actually did see great achieving this. So just moving on. So one of the challenges, though, is when we first started testing it, we actually did have some bottlenecks. And it was interesting because I was on a con call with Paul and Jason and the other DDN guys on the East Coast, and they were saying, hey, we're seeing some weird performance. We can't seem to get to the rates that we expected. Well, we started looking at how the IME servers were connected on our IP fabric, and we noticed that I wasn't necessarily involved at the very beginning, but they actually had connected 12 of the IB ports to a single IB switch, which only had 8 uplinks to the port fabric. Well, of course, that's oversubscribing the uplink. And we realized this. Luckily, we had enough spare ports on some of the leaf switches that we could redistribute all the IME links throughout the switches, put 4 links on each switch. And then we did actually sustain and hit the performance target of almost 80 gigabytes a second after moving these IV connections. So just be aware, as you do deployments, you want to really think about where you're connecting your IO storage on your IV fabric. It can have a pretty big impact, and you don't want to oversubscribe it. So I do have some actual numbers here. These were generated by the DDN team. We took 1,000 nodes on Stampede and said, okay, let's see what we can really do once we run some real applications on it. And what you have here is the columns with the IME write performance, the read performance, and then the back-end parallel file system read and write performance. And as you can see, as we scaled up with clients, one of the interesting things is we pretty much sustained the constant rate on the IME performance of about almost 70 gigabytes a second. Yet, as we started increasing clients in the parallel file system, you can see it did scale out, but really didn't sustain anywhere near the capability that we were able to get out of the 8 IME servers here. So, what really impressed me about this is basically the performance we're getting out of the 8 IME servers would be equivalent to about 25 of our actual storage servers. So here we've got 8 IME servers, and we don't have to deploy as many storage servers to get the performance. But we do need the capacity, so we do need lots of spindles for capacity still on the system. So you see here we've got about 3.7 to 28x improvement on the writes, and about a 6.5 to 11x improvement on the reads. This was the HACC cosmology kernel I/O. So this was a simple I/O test with a cosmology kernel. We also did the S3D testing at scale. Again, here we wanted to see what happened once we really ran at large scale on the system. And again, you see very similar trends. The IME write performance did continue to scale up as we went from one server up to 1,000 cores. And of course, the parallel file system really couldn't sustain the same level of performance. Here, this is a kind of a limitation, I guess, was S3D and their NPI-IO, the way they're doing the I/O. And I think that we did tinker with some of the striping that we did on the file system to try to get some better performance out of the parallel file system, but we could never get it anywhere close to what IME was able to deliver. And again, you see acceleration numbers of 10 to 20x. Of course, this is critical for us. Now we can now think about, hey, we can deploy some of these IME servers to sustain the bursts that we see on the system every once in a while, yet still have plenty of capacity on the back end and still support the large amount of data our users generate on the file system and be able to handle the very high I/O loads that we see at TACC. And finally, we did the Mad Bench. And in this case, it has a couple of different write and read options. Again, you see here, we're actually sustaining what we thought would be the theoretical performance of the IME system on Stampede. Again, comparing to the parallel file system, we're nowhere close. We're getting 10x performance improvements with IME on this true I/O benchmark. So in summary, this is one of our challenges. We keep getting this exponential rate of capacity needs and storage requirements at TACC. I'm sure every other center is encountering very similar issues, and we want to be able to keep up with the rates, but not have to throw a whole lot of servers at solving some of these problems. We can do a whole lot of capacity with fewer servers. So one of our thoughts is, of course, we're investigating IME for future systems, and we want to make sure that we can deploy and handle the very fast I/O rates that they make available. And really the IME testing really demonstrated scalability and capability on a large-scale system. We do plan to do some more testing on Stampede with the 8 servers we have. I actually now wish I had more so I can really do some IO scalability testing, but I got to talk to DDN about that. I see George has already helped me out here. And of course we want to grow it all the way out to the full system. The challenge with the full system testing is we probably really want to pull that off during the system maintenance, and so we're trying to schedule system maintenance upcoming that we can work with and do the full scale system testing. But we're very pleased to see, usually one of these brand new technology demonstrations, you hit several stumbling blocks. I know the DDN guys did a lot of work on the back end to make sure everything is working perfectly. And of course, once we finally figured out the bottlenecks with the InfiniBand network, it really showed the capability that IME can do in a real production environment. With that, I'll wrap up. I'm happy to take any questions.
All right, thanks, Tommy.